Hello class, good evening. Can you hear me? In the meantime, if someone has any question with the previous class, I hope you guys enjoyed the last class. It was on the introduction part of geophysics. In the meantime, when others are joining, guys, you know that in your competitive exams, like geology is something which everyone can answer, right? Easily with your level of education, with your level of practice. But geophysics, this subject or this syllabus of geophysics, becomes such a crucial part that it becomes a deciding factor within the scorers or the rankers, right? Let's say if there are 6 or 8 questions on geophysics, the person who has practiced geophysics well or understood it well will be able to answer those questions. And the person who has correctly answered all them will score more, and that's how the top scorers will be distinguished. I want you all to utilize this 1.5 hour to learn and practice with me the subject geophysics. And meanwhile, when you are doing this, the easiest thing is to just pay attention in this 1 hour class. And I can assure that at least 70-80% of the things you will get within the class. You won't have to spend more time on it. Someone has joined with the name A. Is this a student or is this admin, Omkar? No one responds in the class. Feels like I'm talking to robots, huh? Thank you, Mr. A. It will be good if you can rename yourself so we can interact more, right? So today's class, we will focus on the first method of geophysical exploration, that is gravity. है ना? Let me share my screen. Has someone any doubt from the first class, the first lecture we had on Saturday? Okay, then I have a lot of questions to you guys from the first class. Can anyone tell me? Let me share my screen. Meanwhile, can anyone tell me this method of gravity or geophysical exploration gravity method is based on which physical property, petrophysical property? Guys, speak up, otherwise I will lose interest and then I will not enjoy speaking to you guys and teaching you, and then there will be no outcome of it. Can you see my screen, guys?
Yes, sir.
Okay, so what why I was asking is, can anyone tell me this method, gravity method of geophysical exploration, is based on which petrophysical property? Thanks, Pooja. This is based on density. Thank you. So this is the first topic and a very easy topic, I will say. Archana, it is not anomaly. And the density and anomaly are two different things. When we say petrophysical property, it's only density. Okay. And when there is a survey which is capturing this petrophysical contrast, that is density, and where you see a lot of variation or contrast within this petrophysical property, that's when you call it as an anomaly. Anomaly is nothing but a geophysical term where it stands for it stands for enormous behavior, or something which is not common, or something which is not specific, abnormal. Thank you, Pooja. So don't get confused between density anomaly and density. Density is a petrophysical property, and density anomaly is a abnormal variation within the geophysical or gravity survey. Okay, so let's start with gravity method of geophysical exploration. This is the most common and widely used geophysical survey and one of the oldest methods in geophysics. So the whole curriculum will break it into, we'll start from understanding the principles, then we will go into the data acquisition, survey and all, survey planning and all. Then there is a hell lot of corrections which we do in gravity survey. Step by step, we will see these corrections and the reduction of gravity data. The third topic will be very critical because this is from where you will be seeing. Oh, okay. This is from where. Okay, let me razor. Okay. This is from where you will be seeing a lot of numerical questions in your exams. Then we'll see the interpretation side. This is also very critical because this is where you will see a lot of questions in your paper, on the theoretical front, also on the application front. Then we will see how this gravity method is helpful in the application of mineral exploration, hydrocarbon exploration, engineering geology, and regional studies of Earth structure. Guys, are you with me? Let's start. Quick thumbs up. Thanks, Pooja. So introduction to gravity method. So as I said, this gravity method of exploration is one of the oldest and most widely used geophysical technique. Why oldest and the most common geophysical technique? Because this is something which all the scientists learned in the initial stage of research and the initial stage when there was a lot of demand for understanding the Earth's geometry, to understand about all minerals or where they can get petrol, hydrocarbon, study of the structure of Earth. So when someone wants to join, wait. Sorry. So this was the time when a lot of scientists were exploring on this front. And there was this very famous scientist, Newton, right? What was he doing, guys? He was just sitting below a tree, watching an apple fall down, and then all of a sudden he came up with the most important equation in physics. That's gravity. So when that pop up in the science fraternity, everyone started exploring more, knowing more about this physical property or this phenomena. So from there, it all started evolving. This gravity method is a passive method. Remember, guys, take a note of this. No? This gravity method is a passive method of exploration. Meaning what? Meaning it does not require any active energy source. What do I mean when I say any active energy source? That means that we do not have to generate, or we do not have to have a transmitting energy to measure the gravitational contrast or the density contrast. So this is a physical property of Earth itself. Okay, Earth has a gravitational field, and using that property of Earth itself, we measure the contrast. So this is a question most of the time people in competitive exam it is asked, which are the methods which are passive in nature, which are the methods which are active in nature. So magnetic and gravity are passive in nature because the energy is there in the system. When I say energy, I mean the magnetic field and the gravitational field is there in the system. Hannah? And what are the active sources or the active methods of geophysical exploration? Those are the electrical, electromagnetic, seismic, where we pump in the electrical energy, we generate the seismic waves. Hannah, guys? Take a note of this. Gravity is a passive method. Also, magnetic is also a passive method. Okay. It measures natural variation in the Earth's gravitational field caused by difference in density of underlying rocks. We'll come to it, the density of underlying rocks. These variations are extremely small. We'll again see how small these are, and you'll be surprised to know. These variations are typically very small, of an order of milligal. Milligal is nothing but a unit which we use to denote the gravity measurements in the survey. We'll talk about milligal in more detail in the upcoming slides. But the precision of instruments, they are what the instruments which are very sophisticated, and that's what makes it more easy to capture these small variations as well. And that's how it helps us to understand the geology and the subsurface structure, which are being caused by the presence of some sedimentary basin, some ore body, or any kind of intrusive rocks, or presence of fault, shear zones, salt domes, regional structure of the or the architect of the earth. Someone wants to join. Okay, it all. So the overall objective of the gravity method in exploration geophysics is to interpret the gravity variation in terms of the density distribution or the density contrast, and then translate this variation into meaningful geological interpretation. Right, guys? Any questions on this slide? Any questions on this slide, guys? Okay, then I have a question for all those who are actively listening to me, Tarun, Ankit, Pooja. So there is this example I quoted, no domes, you know, fault and fault domes. So let us say that we are doing a gravity survey in oil and gas for our oil and gas exploration. You know, if you are aware or if you understand the formation of oil and gas, if you understand the formation and how the oil and gas deposits occur, you can recall that most of these oil are oil and gas deposits are trapped by faults, है ना, in the sedimentary basin. Salt dome is a typical structure we look for when we are exploring for oil and gas. Can anyone tell me why we look for salt domes or these dome structures? Or we look for the faults? Because they act as a trap. You can unmute yourself, na? Can you unmute yourself and talk? I think typing will take a little time, na? So you can unmute yourself and we can interact. Yes, it acts as a trap for the oil and gas, and that's where these tend to occur. And the salt domes are one of the characteristic trappers. So using this method, a non-invasive or a quick method, gravity method, we can tap within a sedimentary basin where geologically there could be a presence of or occurrence of oil and gas. We try to locate where are these faults, where are these salt domes, other dome structures. Moving to next slide, guys. Mm, There, as I said, there will be a little bit of physics and math. We cannot skip completely physics and math when we are dealing with gravity methods, right? Or sorry, or with geophysics. So the basic law which governs this entire method of exploration is the Newton's law of gravitation. And the entire physics of this method is based on this single law given by scientist Newton. So this can also be a question in your exam, that which are the laws, like electrical survey is governed by which law, gravity is governed by which law, magnetic is governed by which law. So out of that, gravity is governed by Newton's law of gravitation. So what Newton said? So Newton said that any force is a response of any force between two body is, as you want me to explain, or you understand this? Okay, I will explain. So Newton said that any force between two mass of different mass, or if they are at two different points, can be given or denoted by this first equation, equation number one, where capital G is nothing but the gravitational constant of Earth, which is 6.67 into 10 to the power minus 11 Newton meter square by kg square. And that capital M is the mass of Earth and small m is the mass of the body on which the force is exerted. And then it is inversely proportional to the distance between that two objects. So there is Earth, there is Moon, right? So Moon is on Moon there is some gravitational attraction which has been pulling Moon towards Earth. The distance between Earth center and Moon center is nothing but the r, and small m is the mass of Moon, capital M is the mass of Earth. That's how Newton derived it for Earth and Moon. The same equation lies for any object or anything which is on the Earth's surface. Like we are standing on Earth, we are also executing, or we are also facing, or we are also feeling this effect. Huh? That is the second equation, F equals to ma. Hello. Tarun, you have any question? Okay, I will move. So there is
No,
one
sir.
more
It's
equation.
by mistake, sir.
Okay, okay. I'm not, you physically explaining this to, or I'm not digging down into how these equations derive, because that's of no meaning for you guys, neither from the exam point of view, neither from this class point of view. So there is this one more equation, which is F equals to ma. Combining these two equation, first and second, what this second equation, you may face some of the numerical from the second equation, where a mass of the body will be given, acceleration value will be given, or the force will be given. You would have to compute one of these. So force which has been exerted or which has been felt on any body is nothing but a product of its mass and the acceleration, small a. So when we combine these two equations, when we put m equals to, f equals to ma in equation number one, ma, small m gets cancelled out, and then we get this equation a equals to g capital M by r square. So keep in mind these three equations, equation number one, equation number two, and then when we combine equation number one and two, we get this a equals to capital G capital M by r square. So this is nothing but the Earth's gravitational acceleration, where capital G is nothing but gravitational constant of Earth, which is 6.67 into 10 to the power minus 11. Capital M is the mass of Earth, and small r is the distance of Earth's surface with respect to the center of Earth. Okay, so you know what is the radius of Earth, you know what is mass of Earth, you know the capital G constant ka value. That's how we get this value of 9.8 meter per second square. And that is nothing but small g. Okay, you are with me, guys? Quick thumbs up. Okay, thank you. So on Earth's surface or equator, this is what the value we see. This is an average. We are not going into the detail. We'll go into the detail of this 9.8 in further slides, like how it is different at equator, how it is different at pole. So a local variation in G will cause a local variation, will be caused by a local variation of M or R. Okay, this is a very critical statement, guys. Now read it or listen to it in more detail. A local variation in G will be caused by local variation in capital M or or the smaller. Means what, guys? The the acceleration in gravity, this value 9.8, will vary if there is change in the mass of Earth or if there is change in the radius of Earth. Then where we see this change? in the mass and the radius. We see this change when we are, let's say we take the example of Mars, when we are in, let's say, in seabed, है ना, sea floor. So there the mass of Earth is less because the crust thickness is less. So the M will change. Okay. But at the same point, the R can be constant. In the same way, when we are moving from equator to pole, the capital R will, or the small r will change. At the same point, both M or R can remain constant or can vary. You take this or you try to understand this with a example that, let's say you are standing on a pole, where R is low, where R is small. Because this equation, gravity is inversely proportional to the distance. When R will decrease, acceleration due to gravity will increase because of the inverse relation. So pole, we generally see the acceleration due to gravity is close to 9.98 or something like that. Okay, that much basic is good enough. So when we are dealing with the measurement of gravity in the survey, we rely on few of the measurement units. Okay, so this meter per second or centimeter, oh sorry, meter per second or centimeter per second will not serve a basis for our survey. Why? Because these are too big to be understood when there is a small change in the density. है ना? So a geological variation in gravity are extremely small, as we have seen in the last slide, compared to the Earth's total gravitational field, that is small g. So specific units are used in gravity measurement in gravity exploration, gravity method. The standard unit which is used is GAL, G-A-L. Sometimes it is denoted as small g as well, GAL. This is nothing but short of Galileo, where 1 gal equals to 1 centimeter per second square. ठीक है, ये जो yellow highlighted है ना guys, yellow highlighted are the important, are the bold topics, है ना? Units का difference, or what does 1 gal mean, or what does 9.888 gal will mean. This can be asked in your exams. However, this is too large for a geophysical anomaly. So the value, when you break it down, gal, you take it to milligal, which is nothing but 1 to the power 1000, 0.001. Okay. This unit, milligal, is something very common in the gravity measurements. Okay. Sometime for even finer measurements, we also go for microgal, which is nothing but 10 to the power minus 6. So milligal is 10 to the power minus 3, microgal is 10 to the power minus 6. है ना? In practical surveys for mineral exploration and petroleum exploration, gravity anomaly usually ranges from few milligal to few tens of gal. So we are talking about any value which is in few millimeters or few milligals. है ना? The change. Whereas the regional anomaly will exceed couple of hundreds, 100, 110, 200, 300 milligal. Are you able to visualize this? Okay, then let us see on the last line. Understanding this unit is critical because gravimeters typically resolve change in small. So what is the resolution of all the gravimeters being, or the ideal gravimeters is 0.01, 0.001. The more the accuracy, the better the gravimeter is. है ना? So now you see this part, like let's say 9.8 meter per second square. This is nothing but 978 gal. As I said, 1 gal equals to 1 centimeter by second square, and this is meter per second. You are doing nothing but converting it into centimeter per second square. To convert this in centimeter per second square, you are multiplying both meters and centimeter. Meters by 100. So you are getting it 9.78 gal. है ना? And then to convert it further into milligal, you are multiplying it by 1000, right? So see, the decimal place has shifted by 3. And then again, when you are converting this to microgal, you are multiplying it by 10 lakh. So the gravity place or the decimal place is further shifting by 3 decimals. है ना? So you see guys, we are measuring a change at the 10th place. है ना? जबकि अर्थ का ग्रेविटी इज 9.8 और इक्वेटर पे वो 9.9 हो जाता है. सो दैट सटल वेरिएशन वी हैव टू कैप्चर इन ग्रेविटी सर्वे, है ना? It's very sensitive and it's very small, hence you need a very precise instrument to capture this change. Now let's understand the relation between gravity and density contrast. So gravity due to acceleration is 9.8. And why this difference is coming up? It is coming up due to the density variation of the geological property which is present there. So what happens, what actually we are measuring, or what actually this change in gravity or change in any value indicates to us, and why and how we are doing it in the practical survey. So gravity anomaly in any survey arises because of difference in rock type and different density. So as in if you have a massive or igneous rock beside a sedimentary rock, there will be a contrast in the density. And therefore the gravity method is ideal to map the density contrast, as in you are in a sedimentary basin and then you want to map up some contact, you want to map up some or you want to delineate the major uh, uh, what you want to say, the lithological breakage or the lithological change within a regional scale. That's why this is more helpful, है ना? So a higher density material will show you a positive anomaly, whereas a low density material like sedimentary filled basin, salt domes, fracture zones, cavity will show you a negative anomaly or a low density. Okay, guys, you are with me?
Yes, sir.
Ayush. Okay, thank you. So there is a little math again coming up here is measuring gravity. है ना? So what actually we are doing, guys, in the instrument is nothing but मतलब using the same or the fundaments which we were seeing the equation F equals to ma. So what it is basically, this complete sentence is basically saying is, if we suspend a iron ball, let's say an iron or a metallic mass, we suspend it with a spring, है ना? If there is a change or variation in G or density, then what will happen? This mass will either be pulled down or be relaxed, है ना? So there will be a change in the length of the spring. ठीक है? So that small change is nothing but the response of the change in the gravity within that location, G. And trust me guys, this is very, 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 very small. Hence this first statement, which is 0.000001 gal. है ना? This is that small, 10 to the power 8 and 9, sorry, 10 to the power 8 and 10 to the power 9 of that value. So it's very difficult to capture this small change. है ना? So in summary, what we are doing, in summary, the measured parameter is the force of the mass m due to the presence of another mass, capital M. The recorded parameter is acceleration, which is nothing but in the unit of milligals, है ना? Not in meter per second square. The interpreted parameter is usually density or the causative buried material or the structure which is causing that small change. Guys, you have any question on this slide? No questions?
No, sir.
Okay, let us move forward then. Can you see my next slide? It is on
Yes,
gravity
sir.
instruments. Okay, thanks, Tarun. I think only Tarun has joined or is physically present in this class. Other all are dead. या फिर join करके छोड़ दिया. Archana, you are with me. An Aniket Behra,
Yes.
Ayush. You know what I did? I thought you let me not put that practical questions on slide. Let me ask you guys in the live classes. है ना? And then I'll give you a list of questionnaires when we'll be finishing this topic at the end of the class, maybe in next class or the coming classes. ठीक है? So now, till now, what we have seen the basics, we have seen the principles, है ना? We have seen the physics behind it. We have seen the equations which are driving or which are causing this gravity method in total. Now let us come to the instrumentation part. है ना? So to measure this change, small change, this vital and very small change, we need a very sensitive instrument. So that's why this instrument, gravity instrument, becomes a critical thing to understand, and also a question in exams that what kind of instrument we can use to do what kind of work. है ना? So see on slide, I have highlighted two things. One is absolute gravimeter, one is relative gravimeter. And as the name says, absolute means something which is very specific or something which is particular to or particular about a very specific object. And relative means what? Something in reference to something, right? Like relative. So in gravity measurement or in exploration, gravimeters rely on two phenomena. One is the absolute measurement and one is the relative measurement. Okay. So what is absolute measurement and what is relative measurement? Nothing but absolute measurements, like simply like if I have to put it in very basic or generic way, absolute gravity meters are those gravimeters which measure the g, small g, acceleration due to gravity of Earth at any point on Earth. Are you getting me, guys? So absolute gravimeters are nothing but those gravimeters which help us to measure the change in acceleration of gravity at any point on Earth, which is nothing but that small g ka value, which is 9.869 blah 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 whatsoever. है ना? 9.8 g per, sorry, meter per second square. That value. है ना?
Yes,
Can
sir.
someone tell me why it is important to measure that value? Why we at all want the absolute gravimeters or that value?
We will use it as a standard.
Good, good. Thank you. Yes, it is used as a standard because small g value goes into the calculations and corrections. So if we have to very precisely measure even a small change which is at a 10 to the power 8 or 10 to the power 9 scale, we need this instrument to be very specific. So they work on the principle of something called as quantum physics, है ना? Where you have lot of lasers and interferometry. That's the terminology used in the instrument, where you have where what we do is we pump in lasers, है ना? And as the protons or the neutrons interact with the colliding neutrons, they fall from their orbital origin. So it's very complicated, but you just have to remember this one point, that these instruments are highly accurate and sensitive. And by measuring this g, small g, what we do is we use this mainly in geodesy rather than routine exploration. Anyone can tell me what is geodesy? Pooja, Aniket, Ayush? I want to hear from Ayush now.
Sir, it is the shape of the basic shape of the earth without like water and uh, uh, irregular shape of the earth without water.
Uh, irregular shape of Earth without water. So if I remove water from surface, is Earth of a very irregular shape? That's what you want to say.
Like the topographic heterogeneity is more seen, like it is not more uniform, like we see not a very perfect shape.
Okay. So you mean to say that we are trying to map the actual surface of Earth, right?
Yes,
Okay. Okay. So geodesy is nothing but it is a scientific terminology. Someone can Google it and give me the perfect definition, but nothing but study of the structure of Earth. That if I am correct, maybe I would have to Google it and see. No ways. But this is used in knowing the exact gravity values of Earth, and based on those values, we try to map the subsurface or the bottom bathymetric study when we are in oceans, right? So these absolute gravimeters are used for geodesic rather than routine exploration. If someone has read the slide or gone via the slide, the other terminology is relative gravimeters. है ना? What these instruments do, guys? They only measure the difference in the gravity between the location. The most common instrument for exploration are the spring-based gravimeters such as Syntrax, CG5, CG6. Syntrax is nothing but the name of the company, and CG5 and CG6 is nothing but the name of the gravimeters. 5 and 6 stand for different model numbers. Okay. So relative gravimeters are something which we use in our exploration activity. What they do is they do not take in care of the small g value. है ना? Let's say at a place, let's say here, wherever you are in Orissa, okay, you have both absolute gravimeter and you have the relative gravimeter. Okay. So a absolute gravimeter will give you the value of acceleration due to gravity in Orissa. Let's say wherever you are at your home. I assume that most of you are from Orissa. Okay, and wherever you guys are from. So absolute gravimeter will tell you it is 9.98760.38.382 so. Okay, but a relative gravimeter will tell you it is 10 gal, 12 gal, or sorry, milligal, 15 milligal or so. So what is this small value which is this relative instrument is giving you? Is nothing but the difference between the small g and the gravitation which the Earth is exerting on that place because of the presence of the local geology or the local denser material. You got this? You want me to repeat absolute and relative? Hello. Okay, I'll
Yes,
move
sir.
on. You want me to repeat, Tarun?
No, no, sir. We'll move.
Okay. So in both the cases, absolute, okay, absolute, in both the cases, absolute gravimeter and relative gravimeter, the instrument is very sensitive towards the calibration. We will see to it what happens if it is not calibrated properly in the coming slides. And it is also very sensitive towards the measurement values. Even if it is varying by a 1 or 2 milligal, it will give you a complete false indication. है ना? So the modern gravimeter incorporate sophisticated electronics that improve the stability, reduce the drift, we will see what is drift, and increases the sensitivity of the instrument. So remember this, that gravity instruments are, or most of the geophysical instrument in that case, are very sensitive and electronically very sophisticated in nature. Gravimeter being one of the most sensitive and sophisticated in nature. We'll come to this reduced drift, this terminology drift in the coming slides. So as we have seen in other, like in our previous class, gravity is something which we can measure from air, we can measure on ground, we can even measure it on seafloor or the oceans, है ना? So it can be ground based, airborne or marine, है ना? There are some satellites also which we are capturing the gravitational pull of Earth, the small g variation in the gravitational field of Earth, and those missions, the satellites which are specifically flown for this gravity measurements are called the gravity measurements or the gravity missions, and few of that names are GRACE and GOCE, है ना? ये भी पूछ सकते हैं एग्जाम में कि सैटेलाइट बेस्ड ग्रेविटी मिशंस कौन से हैं और उनका कॉन्स्टलेशन का या फिर वो दो मिशंस का नाम क्या है. तो one of that very famous is GRACE, GRACE, and the other is GOCE. And what they do, they provide the regional gravity data, and then these regional gravity data enables us, or the scientists enable them to understand the structure and map the conventional scale of these structures. Guys, you are with me?
Yes, sir.
On the right side, there is a small image. I have just given it in to explain you that when you are seeing your like prepare career exam के लिए, you can just quickly go through it. So one is absolute gravimeter or the absolute measurement. One is the relative. This is used for geodesy, है ना? And it is based on the laser interferometry, है ना? And it measures the absolute G value. The other one is relative, which is used in exploration work, and it is a spring-based gravimeter. The name of this gravimeter is Syntax CG5, CG6, and it measures the relative change in the gravity. The other one are satellite, GRACE, and already I have told you. Guys, there are where in past there were other instruments as well. There is now Syntax is coming into picture. Syntax CG4 was there. Now people are using CG5, CG6. But there was one more company called as Lacasto, Lacasto, Lacasto. So those companies were also into gravimeter manufacturing. But now there is this company which is producing more and more sensitive gravimeters, and I'll say till 2000 people were using like a stogravimeter. So back in the era of World War, back in the era of oil and gas exploration, Lacusto and even previous versions were used. Now most of the places you will find this CG5 and CG6. So in your exam, if you see any question where it is asking you the name of the gravity meter or gravimeter, so remember that there is one more, Lacasto, Lacasto. It also works on the same principle on the spring-based. It is also a spring-based gravimeter, but the only difference is the sensitivity. It is in the range of tens of milligal. The sensitivity is in the range of 10 or 1 milligal. Here, it is in the range of 10 to the power minus 2 to the 10 to the power minus 3 milligals. Okay. So let us try to link the gravity measurements with the density. Okay? Because density is the petrophysical property which is responsible for the variation in the gravity field or the gravity anomaly. And because the gravity method relies on density contrast, right, guys? So understanding the typical rock density or the mineral density is also very critical or crucial. A sedimentary rock such as sandstone, shale will typically give you a density contrast of 2.0 to 2.6 G per cm cube. ठीक है? While crystalline basement rocks like granite, gneiss will give you a density variation between 2.6 to 2.8 G per cm cube. Mafic and ultramafic igneous rocks such as gabbro, PDT, these will give you a density contrast of 2.8 and 3.3. So I have given you a range of density values for different rocks and minerals. Okay. It's important for you guys to go through this list. This can be as extensive as you want. There are other sources as well, but I have used this source by PV Sharma. This is very common and mostly used of density. है ना? Guys, you're with me?
Yes, sir.
Hmm. So can anyone tell me why I am saying that sandstone and shale will typically range from 2 to 2.6 G per cc? Hmm? And also I am saying that sand and this sandstone is of a density value 2.15 to 2.4. Have you guys calculated density of any rock or any mineral? I'm asking that can anyone tell me why these density values I am giving this density values or these petrophysical properties? Or let me reframe my question, how these density values are coming up of 2, 2.5, 2.8. Have you guys measured density in lab somewhere? If anyone can recall
The specific
Archimedes
gravity
principle.
experiments.
By by specific gravity
Yes.
experiments.
Okay, good. Let me clear one more thing, है ना, Tarun and Ayush. Specific gravity, there is a difference between specific gravity and density. Okay? So specific gravity is a unitless, or specific gravity has no unit to it, whereas density has a unit to it. Okay, let me
Yes,
ask you
sir.
a very basic question. So if you find a basalt on Earth and if you find basalt on Mars, so what will be the density of basalt on Mars and the density of basalt on Earth?
So is it something
Remember, I am saying
related to
density.
magnetic field?
No, no. No, Pooja, density will not remain same. If you are measuring density of basalt on Earth and if you are measuring the density of basalt on Mars, it will give you two different values. Specific gravity will be same. What you said, SG, specific gravity will be the same. So I will give you this homework to you guys. Find out the difference between specific gravity and density. You see in the equation itself that it is gram per cc, right? So it is a relative
See,
value. Someone was saying anything?
yes, sir. Like we have specific gravity, then we calculate it with water's gravity, like 100 gram per cc. So by multiplying with water's gravity, then we'll calculate this gravity.
We will
Then
calculate this.
then giving it these units.
Okay, if I have understood it rightly, Tarun, let me reframe just what Tarun said. Tarun is saying that we are measuring the weight of this rock or mineral with respect to
The
the weight of the same
specific
rock or
gravity.
mineral. Okay, so specific gravity is something different, na, Tarun? I'll explain you. Give me one more minute. So density, what we are doing, density, what it is very simple Archimedes principle that you are measuring the same physical property of a material in two different scenarios or in two different situations. So one, you are measuring it in air, one, you are measuring it in some other reference material. It can be wax, it can be water, it can be any oil as well. है ना? So on Earth, the specific, now I am saying the specific gravity, na? So the specific gravity of water is something very close to 1. So that is the reference we are using. So once we are measuring the weight of any rock or any mineral in air simply एक weight meter लेकर के, and second we are measuring the same value in water, right? Tarun, you are with me?
Yes, sir.
Hmm. So this relative thing, this relative change in the value or the weight will give you will give you the density or
Volume.
specific gravity. Yes, volume. So volume is something which will change. है ना? Or volume is something where you just introduce the cc. है ना?
Yes, sir. So yeah, this density is the mass upon volume only, na? Why
Hmm.
doing weight? Why doing weight of the rock? We measure the mass,
Yes.
and then why measuring it in the volume of water? Why in the water? Then we calculate
Hmm.
the centimeter cube,
Density.
and yeah,
Yes.
by the formula of the mass per volume, we will calculate the density only.
Yes. And what about specific gravity, Tarun?
That will like I don't have the now like by the
Go
weight
and
of the
read.
water. Ah, okay, sir.
Go and read. है ना? So I'll just give you an hint that specific gravity is a unitless property. है ना? So what is coming into the picture, which is cancelling out the units. है ना? So I'll come back to my question. If you measure the density, remember I'm saying density, na? Density of basalt on Earth and the density of basalt on Mars, will it be same or different? Let's say Tarun goes to Mars and he tries to measure with the same way he was measuring the density on Earth. He takes a bucket, है ना? Sees how much it will be. Ah, correct, Pooja. It will be different. Why it will be different? Because the pull of or the small g value,
Gravity.
gravitational acceleration, yes, g, small g, it will be greater on Earth, I
Earth,
think.
Earth has more
Yes,
gravity. Earth has more
yes, yes.
gravity than Mars.
Hmm.
Sir, I
And
want to ask
that's
a question.
hmm.
Like, how much of gravity is dependent on magnetic field?
No, these are two different properties, Ayush. There is no relation, or there is a mathematical relation, or I'll not say a relation, but a way we can derive, or mm, indirect relation, I'll say, not a mathematical relation even. Gravity does not depends on the magnetic field of a property. So magnetic field is different, gravity is different. Remember, guys, when I was starting my lecture, I said that Earth has both a gravitational pull as well as, or a gravitational field as well as a magnetic field. So gravitational field is different. That's a unique and unique and intrinsic property of Earth. In the same way, magnetic is different. You know, it is also a unique and intrinsic property of Earth or any planetary, not any planetary by the way, but yes, other objects as well. Got my point, Ayush?
Yes, sir.
But there is a relation based on the observations scientists had and based on the no re- based on the properties which we saw, there is a relation between density and magnetic. We'll talk about it when I will finish the magnetic class. Okay? So from exam point of view, remember or try to remember few of these density values. कौन सा ज्यादा होता है, कौन सा intermediate होता है, कौन सा ज्यादा मतलब बहुत ज्यादा होता है. Let's say galena is the most densest material. Then try to see where the chromite is fitting in, and then try to understand where the different rock types will fit in. है ना? Now, if I have to say, now we are talking from a scale from 2 G per cc to a scale of, let's say, in rocks only, to a scale of 5 G per cc. So that is approximately a change of 3 G per cc, right? 3 यूनिट का ही वेरिएशन है और वो 3 यूनिट में यू कैन फिट ऑल द रॉक्स, ऑलमोस्ट ऑल द रॉक्स. So you try to imagine that कितना small change होने से कितना बड़ा variation हो सकता है, और the causative body can be as heterogeneous as a small change in gravitational volume will bring in. चलें आगे.
Yes, sir.
Thanks, Pooja. Well, now we have finished the principles, basics, instruments, measurement unit, है ना? The density values or the physical properties which is governing the survey. Now we are going little bit into the acquisition. Na? Abhi principles we have covered up. Now we are going into the acquisition. So this is nothing but a simple flow or a workflow of gravity survey. है ना? So when I was talking in my first class, है ना, कोई भी सर्वे में, कोई भी जियोफिजिकल मेथड में, डेटा एक्विजिशन में सर्वे प्लानिंग इज वेरी क्रिटिकल, है ना. तो सबसे पहले वी डू दी सर्वे प्लानिंग कि किस तरह से डेटा एक्वायर करेंगे, कैसे मैं प्लान करूं मेरा फील्ड. जैसे जब जियोलॉजिकल मैपिंग के लिए यू गाइस गो, यू प्लान आउट ना विच पाथ यू विल टेक, वेयर आर द एक्सपोजर्स, है ना, हाउ यू विल कैरी आउट द मैपिंग वर्क. आइदर यू विल यूज अ टेप और कंपास, or you need some sophisticated instrument, है ना, you need a GPS. In the same way, we have to plan all the geophysical survey in the same way. The most common thing in all the geophysical survey is the survey planning. So gravity also, a typical gravity survey also begins with a very careful planning. है ना? Why careful planning? Because there is a lot of thing which is dependent on the acquisition stage itself. अगर प्लानिंग सही से नहीं होगा, डेटा एक्विजिशन सही नहीं होगा. एक्विजिशन सही नहीं होगा तो डेटा जो प्रोसेस है वो सही से नहीं होगा. अगर डेटा सही से प्रोसेस भी हो गया तो द फाइनल आउटकम will not meet the objective of survey and the entire process will go in drain. है ना? तो what we do, we plan the grids, the survey grid कि कितना स्टेशन स्पेसिंग रहना चाहिए. When I say station, it means one observation point. है ना? Guys, you understand when I say station, gravity station. Gravity station is nothing but a place where we are taking the gravity measurement. We are doing a measurement. है ना? So that is called the gravity station. And if we are carrying out the survey in a line, let's say we take a measurement here, then we take a measurement here, then we take a measurement here, and follow on a continuous line, in a continuous line, that is called a survey line or a profile in geophysics. है ना? So we can go for any station spacing between 100, 200, 1 kilometer, 5 kilometer, depending on the objective of survey. So we have to decide what will be the survey grid or the grid pattern. We have to design it, you know, keeping the geological objective in mind. I will ask a question on this at the end of this slide. Then we have to decide a base station location. I've highlighted this base station. है ना? Now you remember I was talking something called as drift in my earlier slides. Pooja, Tarun, Mr. A. Who is Mr. A? Can you answer anything? Let me continue. So we have to decide a base station where we will take a repeated measurement of the gravity field. है ना? The relative measurement. Here we are using relative gravimeters. है ना? We are doing a geophysical exploration, or this is for exploration activity. This is not a workflow for geodesy study. है ना? And this base station is very critical to monitor the instrument drift. है ना? We will see what is instrument drift in the coming slides. But remember, एक क्वेश्चन आ सकता है कि इंस्ट्रूमेंट ड्रिफ्ट करेक्शन के लिए या फिर ड्रिफ्ट करेक्शन के लिए व्हाट इज रिक्वायर्ड, सो यू कीप दिस इन माइंड। तो बेस स्टेशन रीडिंग्स है ना, द वैल्यू ऑफ बेस स्टेशंस और द बेस स्टेशन रीडिंग्स आर रिक्वायर्ड, है ना। And then follow on when we are doing the data acquisition. During the data acquisition plan or the program, the gravimeter is carried to the survey stations wherever you want to take the reading, and the reading are recorded along with GPS coordinate, elevation, temperature, and time. Guys, this GPS coordinate and elevation, also temperature and time, these are very critical factor along with the gravity measurement, because gravity value depend a lot on the elevation. We will see there is a complete correction procedure because of elevation. It also depends on in which time you are taking. It also depends on the temperature, the ambient temperature, as well as the temperature of instrument. Because due to increasing temperature, what happens is the internal temperature of instrument increases, and that causes a fluctuation in the strengths or the fluctuation in the internal electronics of the instrument, and that may behave very haywire, है ना? So once the field measurements are completed, the data undergoes several steps of correction to remove the effect of latitude. We will see this in more detail, to remove the effect of latitude, elevation, terrain, tides, and the instrumentation drift. So from where we are getting this value, instrument drift, we are getting this from the base station values, है ना? After this adjustment, the result is then a Boger anomaly map, है ना? So there was this scientist, if I recall the name correctly, he was Perry Bro or Peter Boger, somewhat like that. So Mr. Boger was the scientist who actually came up with this equation, and on his name, this uh, correction was named, and the anomaly maps are also named on behalf of his name. So it is called a Gruber anomaly or a Boger anomaly map, which is nothing but highlights the subsurface density variation of the causative bodies, which are giving rise to that abnormal gravity variations or the gravity anomalies on the map. The Boger anomaly is then further processed by separating the regional and the residual components. Can anyone tell me what is the regional and the residual component, what this means? And going forward, this is taken for modeling and then interpretation of the geological structures or geological features. Can anyone tell me what is the regional and residual components in a gravity survey? What is regional? What is residual? The name are very common, specific. जैसे नाम से ही सुन के पता चल रहा है ना, रीजनल इज नथिंग बट द अर्थ's response. Yes, Pooja, thank you, very correct. Regional is like something which is standard. Regional is something which is the Earth's response. So a regional gravity value at equator will be, or anywhere on Earth, will be close to 9.8 G per cc. So let me again take an example of Sukhinda Valley. I hope you all are aware about Sukhinda chromite deposit. Give me a thumbs up. Arshana, Ayush? Yes. So let's say you are in Sukhinda, hai na? In Sukhinda belt, and you are exploring for chromite. Because you guys know that chromite is a denser mineral, and it has a high density with respect to the surrounding or the background geology or the lithology. If I go for a gravity survey, I will get a gravity high in this place, and wherever if I will see a gravity high, it is because of the density of chromite which is more, and a gravity high will or probably will indicate towards chromite deposit in subsurface or that chromite belt, है ना? So with this logic, you geologist go in field, and then you start measuring, you do correction, the instrument drift, you remove the instrument drift, then you go for latitude, elevation, all these corrections, and then finally you get the Boger anomaly map, है ना? So when you come to this point, till this point, see, in above points, I have never said that the Earth's response. So whenever you are measuring anything, it is a combined response of Earth as well as the causative body or the local geology, which in this example is the chromite belt or the yeah, mineralization body. So what you will do is you will separate or you will remove the Earth's response, which is a constant or a standard value. So different in different processing, you will just refer to in which latitude you are, where is what is the regional value of this location, and you will subtract that value from the Boger anomaly map, and whatever residual you will see is the response from the local body. So that residual component carries the information of the chromite deposit. समझा क्या guys? Students, did you get this?
Yes, sir.
Okay, thank you, thank you. And when we have the final data, we try to do a inversion of that data. We call it modeling. So inversion, this terminology, there is forward inversion, there is forward modeling, there is inverse modeling. These two terminologies, guys, I will be using very repetitively. Forward modeling is nothing but you have a source, है ना? You imagine a source. Let us say we are imagining Sukhinda deposit. It is a plate type, thick plate type deposit. It is dipping in some direction, and then you take a no density value of that body. Let us say 4.5 G per cc, and then what we do, we try to calculate what will be the gravity response over this known body, है ना? And then we see what kind of data I will be expecting if I will go for the survey in this area. So what we are doing, we have a known, we we have imagined some shape, size, and depth of deposit, depth of that body. We are assigning some density or from physical property of to that body and some physical property to the background, well, yeah, surrounding. Then what we are doing, we are trying to calculate कि इस तरह का अगर deposit है, इस तरह का अगर subsurface है, तो what will be the data which I will be recording, what it will look like, है ना? Then we see whether at all in field I am doing the data acquisition, whether at all I am seeing a response like that or not. So that's the forward. Forward is nothing but known to unknown. And inverse modeling is nothing but you did not know what was there in subsurface. You went, you did the survey, now you are back with your data, you are trying to resolve the subsurface with the data captured. है ना? So you have the data, you are doing some mathematical inversion or applying some algorithm to understand what kind of body of what density will correspond to or will give rise to this kind of data, what I have recorded in field. So that the final output is a model of density values or the density variation in the subsurface. And by that you get an indication of the geological structures or features present below the surface. So guys, this is a typical workflow of gravity survey. है ना? Now let us go into the details where I said the base station, there is drift correction, है ना? There is a lot of correction on the elevation factor, the location, latitude and terrain correction. I am also talking about tidal correction, है ना? So this is the gravity survey is basically very much dependent on these corrections, and there is step-by-step correction we apply to it. We'll see it in more detail. Before going into the processing part where we are correcting the data, let us see a little bit more in the data acquisition phase. So as I said in the previous stage, हम लोग बहुत अच्छे से plan करते हैं survey को, है ना? We plan our station spacing, we plan our, as you're with me, we plan our station spacing, line spacing, है ना? Then we go to field, है ना? The first thing we do is sorry guys. The first thing we do is we must examine the external condition of the survey area, because the gravimeter is highly sensitive to motion, temperature, vibration. So we have to be very extra careful towards the handling of gravimeter. है ना? If there is lot of vibration, if there is lot of motion, it can damage the internal electronics or the internal framework of the instrument. The first thing we do is a base station is selected on firm ground and reoccupied several times during the day of acquisition program. Guys, anyone understood what is this second point? So the first thing we do is we select a calm and quiet area, where there is no background noise or cultural sound. We fix the gravimeter there, and what we do is we switch on our instrument and we keep it there for a point of time. थोड़ी देर के लिए उसको रिकॉर्ड मोड में चालू करके छोड़ देते हैं to estimate the drift of the instrument. है ना? So what is drift? We'll talk about it when I'm talking more on the drift correction part. बट बेसिकली क्या होता है विथ टाइम जो अंदर का इलेक्ट्रॉनिक्स है ना इंस्ट्रूमेंट का गाइस द स्प्रिंग एंड द टेम्परेचर वेरिएशन because we are keeping it for years and several days it is idle non-operational. What happens with time, the length of the spring changes. Even a micro change or even a change on a 10 to the power minus 10 or 11 will cause a big difference when we are acquiring the data. So we have to do this calculation or what was the drift of value. Let's say in 2010 I was using the same gravity meter and I was seeing that I am in Sukinda Valley when I am doing the survey. My values are, let's say, 10 milligel, 12 milligel. But when I'm doing the same survey in 2020, 2025, in the same area with the same instrument, I am seeing the instrument is giving me the value as 10 milli, oh sorry, it was giving us first 10 milligel, 12 milligel. Now it is giving me 50, 52, 58, like that. So what has happened because over the period of time, the length of the string has changed, or I'll not say actually the length, but the electronics has changed and it has become more sensitive and it has lost its internal homogeneity, right? That's why this variation is coming up. So I would have to correct the values. That is the drift correction. We will go to the equations in the later slides of drift correction. For now, you just understand this much. So service station spacings are selected based on the target size. Target size is nothing but your geological objective. What you want to resolve. Are you looking for a big basin? You are doing a regional survey, or it is a very local survey. So for regional mapping, typical station spacing is around 1 to 2 kilometer. While in mineral exploration, we often go for a station spacing of 100 to 200 meter, even 50 meter, 25 meter as well if our body is too small to be resolved. As I said, the station spacing, there is also, if I'm doing not a single line, I'm not doing a 2D profiling, if I'm doing a 3D survey, so there will be multiple lines of 100 meter spacing of station. There will be multiple lines on both the directions. So the line spacing also we define. Typically, the line spacing is 2 times of the station spacing. This depends on the cost factor, the time factor, and lot of things. है ना? So if I'm using a station spacing of 100 or 200 meter, I'll generally go for a line spacing of 200 or 400 meters. Because the lateral variation is less along the strike, and guys, you are with me, the lateral variation of any body is less along the strike of a body, but it is more when we are going across. So the service station are always, or the lines are always across the body. Let's say if I can switch to pen, I'm not using a board. Next class I'll use. Let's say this is a dipping body and this is your surface. So you are taking one station here, one station here, one station here, one station here, dot, 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 and so on. है ना? guys. So as you move from this direction to this direction, your change in the your change in the reading will be more, right? But let's say you are moving along the strike, है ना? Assume this is the same surface and you are moving along the strike, which is in this direction. Your lateral variation will be less. Hence, the line spacing is approximately twice the station spacing. Am I going into too detail? क्या तुम लोग को ये पता है? You want me to explain all these? Pooja, Archana. Okay, thank you. Just stop me. If I'm going into too detail, just stop me and ask questions. So there is also something which is called as microgravity survey. है ना? Microgravity survey is very common when we are using it or we are exploring some engineering structures or engineering features, or we want to explore for some denser material which is just below the subsurface. है ना? So our depth of investigation is shallow, our body shape and structure is small, and we want to map the density contrast at a very small level. So the station spacing is as low as few meters, 5 meter, 10 meter. है ना? So there can be a question, what is the difference between microgravity survey where you use, what is the station spacing? What is the station spacing for regional mapping or a mineral exploration program? You know guys, what GSI does? So GSI का ये एक program है, नेशनल जियोफिजिकल कैंपेन करके दे कॉल इट. इसके अंदर में दे डू मैग्नेटिक एंड ग्रेविटी डेटा acquisition. So at what grade GSI is, acquiring the data of entire India? They are using a grid of, earlier they were using a grid of 4 by 4 kilometer. Means at every 4 kilometer in India, you will have one station or one reading of gravity and magnetics. Now they have reduced it to 1 or 2 kilometer depending on the area, and for regional surveys. And when they are exactly or specifically exploring for some base metal, some bulk commodity like iron, chromite, manganese, lead, zinc, copper, gold, there they are doing gravity survey at 100 or 50-meter station spacing and 100 and 200-meter line spacing. Hello guys, you are with me? So at each station, the gravimeter is level, stabilized, and allowed to settle before a reading is taken. And this is very important in acquisition process of gravity data. So we have to wait, we have to level the gravimeter. Why level the gravimeter, guys? So let's say we have a gravimeter like the, why this is happening so, okay. Let's say we have our instrument on a flat ground. So in this case, whatever I am measuring, whatever change in gravity we are measuring, if it is vertical, then we are measuring the exact response, which is, I don't know why it is happening like this. We are measuring exactly the response below this point. But if my instrument is not leveled, let's say this is little bit tilted like this. I'm bad at drawing, guys. So the response is not from here, it is from here, right? So you are measuring something which is here. So that's why the leveling of gravimeter is very critical thing. So once we have leveled, we allow it to rest for some time. Why we allow to rest it for some time? So that जहां से भी हम लोग लेके आ रहे थे, कैरी करके आ रहे थे, there were a lot of shock and absorption, है ना? तो जो इंटरनल इलेक्ट्रॉनिक्स है, जो इंटरनल मैकेनिज्म है, उसको थोड़ा टाइम देते हैं सेटल डाउन होने के लिए, स्टेबल होने के लिए, है ना? Then we take a reading. We ideally wait for 3 minutes, 2 to 3 minutes, 5 minutes, and we take the reading then. Elevation is a very critical factor in gravity survey. We need to have an exact or a very precise level or elevation information of the station where we are acquiring the data, because this elevation will go further for the processing at this processing stage. So we use DGPS for exact or a precise station. What is DGPS? DGPS is nothing but differential global positioning system. So in GPS, you have the accuracy of, let's say, 4 to 5 meters in X and Y, and in Z value, you have maybe, I don't know, 7 to 8 meters. But in DGPS, the accuracy in X and Y direction is as less as zero point 0.5 centimeter to 1 centimeter. It is not more than 2 to 3 centimeters. And the same goes for Z value. It is between 5 to 10 centimeters, the accuracy. And it matters a lot. That's why we are using such a high precision for leveling or to record the elevation. So now we have seen, now we'll go into the data processing stage. Guys, you're with me? Now this data processing stage is more critical, or the correction of gravity data is more critical from exam point of view, because बहुत सारा numerical है ना इसमें से आता है ना, to calculate the free air correction, to calculate the terrain correction, to calculate the drift of the instrument, है ना. So at the coming slides, there will be little equations. I have not put up the numericals with the slide, because we will take a separate class on the questions and numericals, solving the numericals. I want you to first understand what it is actually, and then it will be very easy when you will be going for the calculations of the numerical problem. है ना? So these are the steps of gravity data correction. What happens is, when we acquire the raw gravity measurement, it is influenced by several factors, as in the underlying geology, the response from different elevation, the response from different latitude, like if you are surveying on equator, if you are surveying on, let's say, somewhere between equator and pole, then if you are surveying on pole, a same body can give you different response of gravity anomaly. Therefore, corrections are applied systematically. Remember, this is systematic, meaning what? You cannot do terrain correction before drift correction. So it is a step-by-step correction. The first correction is drift, then followed by latitude, then followed by free air, then the boger, and then comes the terrain correction. And guys, it's a step-by-step process. So you cannot do first terrain correction or ATOS correction, or then free air, or then calculate the drift. So first the raw values will go for drift correction, then it will go for latitude, then it will go for free air. This sequence is very important. है ना? Exam में पूछ सकते हैं which is the correct sequence of gravity data reduction or gravity data processing. You remember, first is drift correction, then latitude, then free air, then we do the boger correction, then we get the boger anomaly, then terrain correction, and then ETOS correction. Out of this, ETOS correction is very specific correction, and it is applied to those gravity value which is recorded on a moving platform. है ना guys? We will see what is ETOS effect and what is ETOS correction when we will be seeing this processing step. है ना? But remember, ETOS correction is done when you are acquiring the gravity station on a moving platform, as in when you are acquiring the data on a ship, when you are acquiring a data on airborne or helicopter or plane. That's where this comes in. Laser. Correcting all these raw readings will give you the boger anomaly map. After all corrections are applied, the remaining anomaly is for more representative of the density variation in the subsurface. And when you are seeing the raw data, you cannot just directly point out where the anomalies are and what density is responsible for what anomaly. So now let us go into this correction step by step. Drift, latitude, free air. I'll try to cover at least one or two today, because I think we have passed the time. We'll continue for 5 more minutes, and then we'll open for question and answer. Is it okay, guys? Let us at least do drift correction today. Because I have talked a lot about the drift, then I just want to touch on this. So gravimeter are mechanical instrument, and their spring gradually relaxes over time, causing the reading to drift. है ना? This can be a question, guys. So why at all you require to do a drift correction? Because this mechanical instrument, the spring gradually relaxes over time. है ना? मीन्स क्या, उसका इलास्टिक प्रॉपर्टी जो है स्प्रिंग का वो चेंज हो जाता है, द कांस्टेंट चेंजेस, है ना, causing the reading to drift. To quantify this drift, the base station is measured at the beginning and the end of the day, and sometimes periodic during the survey. It's not very common during periodic in survey, but क्या होता है, जैसे आज मॉर्निंग में मैं सर्वे करने के लिए निकला, what I will do, I'll go to my base station location, means that is a fixed location. Every day, first I will go to base location, I will see the value of gravity at that location, and then I will record it as my constant value. Then I will go in field. है ना? When I am coming back, I will again come to base station. I'll see the reading. है ना? Check the reading. अगर मॉर्निंग में लिया हुआ रीडिंग और इवनिंग में लिया हुआ रीडिंग वेरी होता है, तो वी विल सी कि मॉर्निंग में कितना आया था और इवनिंग में कितना आया था, एंड देन वी सब्सट्रैक्ट द वैल्यू. मतलब क्या, पूरा सर्वे करने के टाइम में the readings have gone down or increased by that value. Let's say morning में it was 9.823, let's say it was 10 milligal, and evening में मैं base station में आया and the reading is showing as 12 milligal. So over the survey period, वो पूरा दिन जब मैं सर्वे कर रहा था, तो the instrument has drifted by 2 milligals, है ना, and then we have to correct the entire readings I have taken in the day for that 2 milligal, and I have to adjust it. The drift rate is assumed to be linear over a short period, that is like in a day or in half day or the same day of survey. If the time difference between the two base reading is known, like morning में 8 बजे, evening में 6 बजे, the drift per hour, like from morning 8 to evening 6, this is 10 hours. So every hour, if there is 10 घंटे में अगर 2 मिलीगैल चेंज हुआ, तो every hour it is changing by 0.2 मिलीगैल, है ना, per hour we can calculate. It is we assume it, the variation was linear over the time period. This ensures the slow instrument drift cannot be hello. So this drift will not contaminate our geological anomaly. This is the formula. You can note it down. The drift correction is nothing but the change in small g over a time period. So this del g is nothing but मॉर्निंग में कितने बजे रीडिंग लिया, लेट्स से 10 मिलीगैल था, इवनिंग में जितने बजे रीडिंग लिया, लेट्स से 12 मिलीगैल आया, देन वी डिवाइडेड बाय टाइम, दैट इज नथिंग बट द डेल टी, व्हिच इज मॉर्निंग का 6 बजे, सॉरी मॉर्निंग का 8 बजे, इवनिंग का 6 बजे, कितना हो गया, डेल टी कितना हो गया, 10 घंटा हो गया, डेल जी कितना हो गया, 2 मिलीगैल हो गया, एंड देन वी मल्टीप्लाई इट बाय कैपिटल टी. व्हाट इज कैपिटल टी? is the total time we have taken the observation, है ना. Base station reading before and after reading will be interpolated as drift correction or the drift of the instrument. You understood this? ऐसा हो सकता है कि तुमको 4 वैल्यू दे देंगे, which is nothing but एक सर्वे किया सुबह 6 बजे, शाम को 6 बजे, and you will be given 4 values and you will be asked to calculate the drift. We will do numericals on this, है ना guys, don't worry about it. The next correction is the latitude correction. These two are very basic ना guys. पहला वाला क्या था, drift, ये instrument error को incorporate करने के लिए होता है. दूसरा is latitude correction. You know that gravity varies systematically with latitude because the earth is not a perfect sphere, है ना. It's oblate or spheroidal, है ना, flattened on pole and oblate on or bulged on equators, है ना. So on equator, as you move up towards pole, there will be a change in the gravitational pull of Earth, the G value. As I was repeatedly saying, equator pate is close to 9.7, pole pate is close to 10, है ना, G per cc. Accordingly, what will happen? Accordingly, the centrifugal force caused by the Earth's rotation reduces the gravity more near the equator than the pole. So the value will be reduced more near the equator with respect to the poles. There is a theoretical relation to calculate that, and that is the theoretical value for the correction of latitude. है ना? क्या है दोस्त ये वैल्यू गाइस? स्मॉल जी ब्रैकेट में theta is nothing but that latitude of Earth. Let's say you are at 28 degree, so G at 28 degree. G is nothing but the factor of correction, and nothing but the latitude correction. So we are calculating how much correction I have to do at, let's say, 28 degree latitude. It is nothing but these all constant factors, and at theta you just have to put that latitude where you are at the surface, है let's say you are at 28 degree or you are at 20 degree. So at different latitudes, this will vary. So these all are constants. You just have to put the theta for which you want to calculate the latitude correction, and then calculator kholo, ye values डालो, and then just get the correction factor. है ना? This correction removes the periodical variation of gravity due to Earth's shape, leveling leaving only the local geological influence. At this stage also, it is not the geological influence, but we still have to do the other corrections. है ना? So for today, let us stop at latitude correction. I have already passed 10 minutes. Any questions on today's lecture, guys? मैंने बहुत बोल लिया यार, तुम लोग भी कुछ बोलो. I still don't know who is Mr. A. Thanks for giving that thumbs up. I'll stop my sharing. Stop presenting. Stop presenting. So from next class, na guys, I want you to come up with pen and paper. We will be solving numericals based on these equations within the class. And I will be popping up some questions with the values, and I will ask you to give me the answers. So what will happen, we will be utilizing this 1.5 hour more productively. So you are well versed with the solution. You are well versed with the this let's say latitude correction का जो मैंने दिखाया constants का. I will give you the exact number as well. है ना? बाद में फिर एग्जाम टाइम पे आपको उसको you don't have to go and practice it again. Any doubt from today's class, guys? Thanks, Pooja. No. नो बोला मतलब कि सब समझ गए या फिर कुछ भी नहीं समझ में आया? Tarun has left the class. Ayush, you are with me? I still don't know who is Mr. A. Okay. So before you leave, I want you to go and see what is geodesy. I want you to go and see on little bit on the gravity method of exploration. And when we are coming back to the second class, I think I'll schedule it on Saturday or Sunday. Then we will give practical questions. Come with pen paper. हम लोग उसको also a calculator will solve some real examples and numericals. Any questions? Ayush? Archana, no questions? Thank you. Okay. Then let us call it a day. Chalo, take care. Bye-bye. Bye. Thank you. Thank you. Bye. I'm leaving the class. I'm stopping the presentation. Bye.